There is this theory in number theory that says if you're given any positive integer n, and if you take all of its positive divisors d1, d2 all the way up to dk, and if you take the Euler token function of each positive divisor and you add them all up, you get exactly n. And there are many, many different ways of proving it. Now, I found a really, really cool proof, probably one of the coolest proofs that I found in a textbook that actually doesn't require. So, in other words, I want to prove phi of d1 plus all the way up to phi of dk is equal to m, where d1 divides m all the way, dk divides m, and also d1 all the way up to dk, and m are all positive integers. And so this proof doesn't actually require the use of formula of the Euler token function, where if you use d, fix d, and rewrite d into a unique factorization of powers of primes that are mutually distinct, and you apply the Euler token function and apply the function onto each prime to the power and multiply them together. Doesn't require that. All we have to do is I want to, among the number 1, 2, all the way up to m, excluding 0, because 0 is not a positive divisor. In fact, 0 can never be a divisor. So out of this many numbers, I want to partition them into several mutually disjoint sets, namely E1, right? So this is set, right? Many, many elements. So I take each element out of here. So what do they have in common? Their common property is that x1, so that the GCD between x1 and m is denoted as a1, a fixed positive integer. Right? The GCD, I'm not writing GCD in front of the brackets just to save some space, and so on and so forth. Right? E2, E3, all the way up to EK. Right? This set, many, many elements. And each element in this set, xk, right, GCD between xk and m is equal to ak. Now here's my claim, that all those sets are mutually disjoint. In other words, you cannot find two sets that share a single common element. Why? Because otherwise, suppose if you have some common element A0 that maybe two sets share, right? But notice that A0 and M, their greatest common divisor is a fixed number, fixed positive integer. And since two sets share that element, that means that element A0 and M, GCD is some AJ. And also for the other set, A0 and M, GCD is equal to AI, AJ, AI are different, right? It cannot happen. So every set in here are just mutually disjoint. And also, of course, I categorized in such a way that each GCD is different. So that, right? So otherwise it's meaningless. So also at the same time, I want to claim that D1, D2 all the way up to dk and A1, A2 all the way up to ak are one-to-one correspondent. Right? The reason is because if I take any dj out of these, can I correspond dj to a unique aj here where dj equals exactly aj? Yes. Because if you think about the GCD between dj and m, what is that? Must be dj, right? Because dj divides m, right? It has to be. So in other words, since dj must come out from one of those numbers, right? dj, the positive divisor of n, must come out from one of these. And also, these sets, the elements are just partition of these elements, right? So since dj comes out here, so dj must live in somewhere here, in some set ej, right? Must be a ej. So that according to the property of each set, the GCD between any element in that set and n is exactly equal to fixed positive integer, right? Since GCD of dj and n is already dj, so must be equal to dj for some element, for some set ej, right? So yes. So vice versa, for any aj, can we correspond it to a unique dj here? Right? That is even more obvious. Right? You take any aj out of here. So which means the GCD between any element from that set and n is equal to aj. And so, which means aj divides n, right? Which means aj must be some positive divisor, right? Must correspond to exactly the same dj here. So, right, one-to-one correspondent, without loss of generality, I can rewrite A1 as D1, A2 as D2, all the way up to AK as DK, right? Because otherwise I can reorder them, right? Since they're one-to-one correspondent, right? Reorder them, then they become D1, D2, and DK, right? So this is fine. This is justified. Now, next, I want to have a look at after I divide x1 by d1 and n by d1. What do I have left? So, right? In general speaking, I take xj divided by dj and n also divided by dj. What do I have left? What's their greatest common divisor, right? After divided by dj. Of course, I'm left with 1 on the right-hand side. Right? They must be coprime. Right? This is obvious. For every j, right? J goes from 1, 2, all the way up to k. This is true. And also notice that for every xj over dj less than or equal to what? xj comes from some ej, some set ej, right? It's also comes out from some number in here. Must be less than or equal to n, right, over dj. Right? dj is fixed. Any fixed j. Larger than or equal to 1, right? 1 over dj. No, not necessarily. But overall, xj, and I should say, xj over dj is a positive integer. So positive, of course, larger than or equal to 1. Right, it takes 1. Yes. Since 1 and this positive integer, what's their GCD? Is exactly. Yeah. So it can reach 1. Right? So think about this. Think about Euler token function definition, right? So from 1, 2, 3, 4, all the way up to this positive integer. And this positive integer happens to be coprime to this modulus, right? So how many of them have such property? How many of them? Exactly. So number of xj over dj. So that GCD of xj over dj and n over dj equal 1. How many of them? Exactly phi of m over dj. This many of them. That's the definition of the Euler token function, right? And the question is, does this positive integer xj over dj run through all the positive integer that's in between 1 and this positive modular that's co-prime to this modular? Does it run through all of them, right? The answer is yes. Because the number of such element is equal to the number of xj and m where their GCD is equal to dj, right? Because they're one-to-one correspondent, right? This is before I divide by dj. This is after I divide by dj, right? One-to-one correspondent. So the number of such element is equal to the number of such element that satisfy this condition, right? How many right. So this xj is already all the possible integers between 1 and m such that their GCD is equal to fixed dj. So they're all there. They're all here. So which means every possible integer that's co-prime with this modulus in between 1 and this modular are all there, are all here, right? Because since they're one-to-one correspond. Okay, so now I can say that because for any fixed dj, I know that xj varies, right? In ej, right? There's some ej, some set ej, where xj is some element, is any element, right? So that's why xj varies inside ej. So which means xj and xj over dj are one-to-one corresponding, right? Because dj is fixed, xj varies, right? Those two numbers, integers, are one-to-one correspondent. So which means the number of elements xj so that xj and m over dj are co-prime. How many of them are there? Right? Because like I said, xj and xj over dj are one-to-one correspondent. Right? Right? Also, how many of such positive integers are there so that this positive integer and this positive integer are co-prime? There are this many of them, right? So it must be that how many of such positive integers so that they are co-prime must be the same. Must be, yeah, right? Phi of m over dj, right? And also, have a look at the number of xj so that the GCD between xj and m is dj. How many are there? Right? So this is after I divide by dj. Right? There are this many of them. Right? So this is before I divide by dj. How many of them? Right? Must be also this number. Right? Yes, phi of m over dj. And so that think about the number of xj. J goes from 1 all the way up to k. Add them all up, right? How about that? What can they equal to? Right? Phi of m over d1 plus all the way up to phi of m over dk. What do they equal to? Right? They equal to exactly, right? Like I said, there are this many of them, right? xj, right? How many of xj are there in this ej, right? So that xj and m, GCD is dj. How many of them in that ej? Right? Equal exactly to the number of elements in ej, right? Same goes for E1, E2, right? Right, so which means phi of m over d1 is equal to the number of elements in E1. Phi of m over d2 is equal to number of elements in E2. So the number of elements in E1, E2, all the way up to EK, they add up to how many of them? 1, 2, 3, m many of them in total, right? And I'm done, right? I'm done because m over d1 turns out to be a positive integer. Since d1 divides m, right, how about m over d1, this positive integer as a whole entity? Is it also a positive divisor of m? Yes, of course, right? If 2 divides 8, gives us 4. So which means 4 divides 8, right? So this is also a positive divisor, and so is this a positive divisor, right? So each m over dj corresponds to a unique dj here, right? Some dj here. 1-to-1 correspondence. So this sum is equal to exactly this sum, right? And so we've proven it really equal to m.